Okay. So hello everyone. I'm Xiatao Xu from the Brookhaven National Lab. The title of my talk today is the optimization of lanthanum junction copper oxide single crystal film screws via the molecular beam epitaxy. So firstly, let me give an introduction to the material. So the LSCO is an archetypical Cuprate high-temperature superconductor. So the crystal structure of its mother compound, which is undoped LCO, is shown in the left. So the crystal has a fabricate-based structure that is common for most of the other cuprates, by substituting a certain portion of lanthanum with junction, one can dope this material all the way from anti-ferromagnet insulator to the Fermi liquid metal. So I believe everyone see this phase diagram many times today. So the phase diagram is definitely rich physics, and so far a complete understanding of this phase diagram is still missing, and the understanding of the mechanism of the high TC superconductivity of this material is also not clear. So for us, our motivation is to better study this material, and we believe to study this architectural Cuprate may help us to bring changes in the fundamental understanding of this Cuprate superconductors, and it may help us to realize our ultimate goal, which is room temperature superconductors as well. And our approach to our solution to the problem is the molecular beam epitaxy. So the MBE is recognized as the highest standard of the material synthesis. The principle of MBE is simple. So the solid source particles sublimate, and once they arrive at the heated substrate, they will bind, nuclear, and condense, following the guidance of the crystal structure of the substrate. For the groups of oxides, normally it is equipped with a strong oxidation source, and a QCM is normally equipped in an MB chamber to monitor the absolute deposition rate of the beam flux. A unique tool that is equipped with the all-MB system is a reflective high energy electron diffraction, which is the rate gun. It helps us to realize the real-time surface monitoring during the growth. I also want to mention that with the precise beam flux control, one can realize the layer-by-layer growth in an MB system, which is the highest precision that one can get for the material synthesis. So the actual realization of this simple concept is actually complex. So below is the MB system at the Brookhaven lab. So this system is equipped with 16 metal cells with compute control shutters. It also has a dual deflection rate gun, the scanning cross crystal monitor, and a homemade pure ozone source. The whole system is also highly modularized. It is equipped with over 26 turbomolecular pumps, which means that each part can be maintained and repaired without breaking the vacuum in other chambers. So in one word, the system is specially designed for the growth of cuprates. So next, I would like to introduce some of the important tools in our system. So First one, we have a homemade ozone distillation system. The ozone distillation, the principle of that is using the different boiling temperature of ozone and oxygen. The mechanism is shown in the left plot. We can see that the oxygen and ozone gas, once they were generated from the ozone generator, they will be cooled down in the ozone still by the liquid nitrogen. At a proper temperature, only ozone will be liquefied and condensed and stored in the ozone still, while the other residue oxygen gas will be pumped out. And later, by applying a proper heating, we can supply a pure ozone gas into the growth chamber. The reason why we use the ozone is because it has a very strong oxidation power, and the ozone gas has no kinetic energy once they reach the sample surface, which means they will not damage the sample surface. Another important tool is the QCM, cross crystal monitor. So we perform the QCM calibration for each beam flux every time before it grows. The accuracy of our QCM has an accuracy of better than 0.0001 layers per second, so which is the key to realize the atomic layer by layer growth. So now we have the system ready. It's time to talk about the growth. So the crystalline substrate, they served as the template for the MBE growth. So the preparation of substrate are crucial for any MBE growth. So the LSCO and STO are two commonly used substrates for the growth of LSCO. So I will introduce the annealing recipes we developed for them separately. So for LSCO, we have developed this cation-rich thermal annealing method. As we can see, the as received substrate usually has a defects of height of 5 to 6 nanometers. And by applying this annealing method, after the preparation, we see this substrate, this defects are no longer exist, and the substrate has this clear stepped terraces, and the roughness of the surface only 0.169 nanometer, which means we have obtained the intrinsically atomically flat substrate, and the substrate quality is also confirmed by read in the MB chamber. So it's very similar for the STO substrate. Here we have adapted this two-stage annealing process. As we can see, as received substrate usually are full of defects and doesn't have a clear step. After this two-stage process, we see this substrate has a clear step terraces, and the surface roughness is 0.25 nanometer, which is less than the height of one monolayer. So again, this means we got a atomically flat STO substrate. And a read photo of this substrate is also shown below to confirm the quality of the substrate. So after we have prepared the substrate, it's time to start the MB growth. The principle of this so-called atomic layer by layer growth is not complex. So once we have the substrate, once we have a proper substrate temperature and the chamber pressure, notice that the crystal structure of our material is intrinsically layered structure. So for the ALL growth, basically every time between the shutter open and close, we deposit the exact number of atoms is just enough for the growth of one layer of the material. For example, here we started with a Limestone junction layer. So the Limestone junction shutter opens and then close. After finish this layer, the copper shutter opens and we deposit another layer of copper oxygen. Then the copper shutter close and we start to deposit another Limestone junction layer. So by simply repeating this process, we are realizing this atomic layer by layer growth. And notice that so the height of a monolayer of the LSCO is 0.66 nanometer, which means we are realizing this film thickness control digitally. And besides the single crystal, one can actually change the following layers, the compound of following layers by will, which means we can grow more complex structure than single crystal. For example, the heterostructures or artificial superlattices. Okay, so during the growth, we are monitoring our sample surface condition in real time by the rate. Below is a rate pattern of optimally doped LSCO films. We see there are several important features. First, these 5 mass stacks. They are very sharp and long, which means we are realizing a 2D growth without any 3D precipitations. This speckle spot in the middle is very bright, which means the sample surface is flat and smooth. We also see this diagonal Kikuchi length and the secondary Loy circle, which is only observed in the high quality samples. So in one word, we are obtaining this high crystallinity structure without any secondary phase precipitation. Another important information from the read is the periodic intensity oscillation, which is taking the brightness of the specular spot. So on the left-hand side is a plot of the intensity oscillation. We can notice that each oscillation period is corresponding to the growth of one LSCO monolayer, which means we are realizing the atomic layer by layer growth. We also notice that the intensity of this the peak didn't decay, which means the sample surface is flat and smooth even after many layers. Okay, so next we compare the rate pattern of LSCO film with the LSCO substrate. First, the distance between the mass stacks correspond to the lattice constant. Here we can see that the lattice constant of the LSCO is the same as that of the LSCO, which means we are realizing this epitaxial growth following the guidance of the LSCO substrate. And a new feature which is not presented in the LSCO substrate, you can see is this set band reconstruction. So actually, this is a prominent feature that can be observed in all LSCO films. Let me put this in detail in the next page. So here, I'm showing the rate pattern of LSCO films with different doping levels. As we can see, they all have this kind of set boundary reconstruction, which means that is a universal feature for all the different doping level. But if you look carefully, the pattern of this different doping, they are different. For example, for 0.14, it's a slightly underdoped sample. The sideband looks like a 1 + 3 + 1. For an optimally doped sample, there's 4 evenly distributed sidebands. And for overdoped sample, normally that is 5 evenly distributed sidebands. So atomistic understanding of this surface reconstruction is actually still missing. But at this point, the sideband pattern can provide helpful information for us to check the correct stoichiometry of our doping level during the growth. Okay. And another thing we did to improve our sample quality is we have developed this read and diagnosis strategy for the LSCO. So below is two read patterns during the growth of optimally doped LSCO. We can see that the pattern of this read is also different for the copper layer and the less junction layer. So during the ALL growth, we would expect the pattern A and pattern B replaced by one and each other all the time. So from our experiment, we noticed that the time existence for this four sideband reconstruction in the copper layer is very sensitive to the amount of copper atoms deposited on the sample surface. And there should be a clear window, which is about 10 to 15 seconds. Otherwise, to maintain the correct copper stoichiometry, otherwise the sample may have defects on the surface. So it's natural for us to develop this strategy, which by timing the time interval of this four sideband reconstruction pattern and adjust the Cooper shutter time accordingly to maintain this clear window. So by doing this, we have improved our yield ratio to a very high level. So this is basically how we maintain the correct copper stoichiometry. Next, I also want to mention that there's always a trade-off between the oxidation power and the MBE condition, which means to maintain the UHV MBE condition, the ozone partial pressure sometimes is not at a proper level during the growth. And what happened is it will mostly affect the oxygen content in our film. And they will create oxygen defects, normally that contains the extra oxygen atoms or oxygen vacancies. So a proper post-nailing process are very necessary. On the right-hand side, I'm showing some the effect of some several different annealing conditions. So for different LSCO compounds, we have developed different recipes accordingly based on our study of over 3,000 films in the past 20 years. So I'm not going to show the details of this annealing recipes here. Okay, so this is pretty much everything about the growth. So next one is I would like to briefly introduce about how we characterize our films. So we use the mutual inductance to characterize the superconductivity of the growing film. The mechanism of the mutual inductance is shown in the left panel. The growing film is sitting between two coils. The drive coil is generating a temporary magnetic field, which will penetrate the superconducting film, and the magnetic field will be mirrored by the pickup coil with a locking amplifier. So when the sample is becoming superconducting, we would expect it will screen the magnetic field, and so we will expect a signal change. from the pickup coil. Right one is the real setup for our homemade mutual inductance system. It's everything sits in a software block. So look at the mutual inductance data. Normally, it contains two parts: the real part and the imaginary part. If we look at the real part at the left-hand side, there is a huge drop of the signal at about 36 and 37K, which is corresponding to the formation of a complete superconducting loop. On the imaginary part, we see this peak is built up, which is corresponding to the build-up of superfluid density, and the peak sharpness is a good measure of the overall surface sample homogeneity. So for our sample, the variation of TC within this LSCO films are very small, which means the film is quite homogeneous in this whole whole sample area. Next, we also use the AFM to look at the growing film. So again, so if you look at this AFM image, the sample surface has a very clear stepped terraces, and the surface roughness overall is only 0.17 nanometer, which is less than the height of the monolayer. So again, it means we have grown the atomically flat LSCO film. So in summary, we have prepared the atomically flat substrate. Using this substrate, we are able to grow atomically smooth LSCO films with a sharp superconducting transition. The film quality and homogeneity was confirmed by the read AFM and the mutual inductance. So here I'm only introduced about the growth of the single crystal. Actually, this is like a Rosetta Stone. With this information, we can use that growth recipe to grow more complex structures, such like the heterostructures or artificial superlattices of the LSCO, which can help us to fabricate different devices and to prove the material of the property of this material from a different aspect. And more important, what's more is we hope what we have developed for this certain material could also be a good hint for the growth of other complex oxides to help us to further explore and understand this large family of the material. So besides this, I would also like to give a short advertisement from my colleagues in the group. I think Yuan and Roberta, their talk already happened earlier today, and Tony will give a talk about the method to fabricate LSCO devices in about an hour. On Thursday, October 20, she will give a talk about how we grow LSCO-based superlattices, and using this superlattices, how we can probe the interface issues in LSCO-based trilayer junctions. So I think that's probably everything from my talk. Thank you.
So there is time for a few questions. Yes.
Hi, thank you. I have a
Hello.
question. How take your film And is there some limit to control the atomic layer deposition in your system? Is there some limit of the thickness? For example, can you control the atomic layer deposition while the film thickness is increasing?
Did you get that?
Sorry, I didn't quite get the question.
The question is if you are able to control
Uh-huh.
the atomic layer rate while the film is growing.
Yes. So here. So basically, we can control we can stop growth at each of these layers, which means the highest resolution we can get is a one monolayer, and we can stop at each monolayer by closing shutter. Yeah.
Hi.
Last question.
Thank you for showing us these wonderful experimental techniques.
Mhm.
You showed this measurement of susceptibility, and you saw sharp peak,
Uh-huh.
and then still above this peak there is something which is non-zero. Do you know what it is? You have a tail to the higher
Yes.
temperature.
So it's the imaginary part. I think that's so it's what to say, the film is it's not a perfect insulator. So that's why you still have some response at the imaginary part, because the mutual mechanism is kind of like measuring the complex number of the conductance. So you expect
can
some.
I
Okay.
can I comment? Nevin, this film, this substrate has backside coating, which is metallic, strontium rutenate, and it's a thick film. It's not superconducting, but it's metallic, so it has some skin effect. If we remove that backside coating, then the imaginary part is zero, above and below. It was not corrected for the metallic background.
Thank you.
These are raw data.
So we have to move to the next speaker.